Good morning. I'm Barbara Grosz. I'm a computer scientist on the faculty at Harvard University. My co-panelist, Cliff Nass, is a social scientist on the faculty at Stanford University. Our topic today is human-technology interaction. Cliff and I are both engaged in research that aims to understand and change for the better, we hope, the ways in which technology works with and presents itself to people. We seek to understand what happens at the boundaries between people and technology, the kinds of connections and interactions that go on, the ones that work and the ones that don't work, and to ferret out the characteristics of human cognition that make certain kinds of interfaces better than others. We agree that making computers smart is hard. We also differ. Our approaches and the questions we ask reflect our different disciplinary backgrounds. To characterize somewhat oversimply, Cliff, a social scientist with particular expertise in social psychology, seeks to make machines appear smarter even when they're dumb. And he thinks people should adapt or be subtly coaxed into adapting to systems. I'm a computer scientist, and I want to make machines behave smarter, and I think systems should adapt to the people who use them. So you'll hear similarities and differences as we talk about our work in the first 20 minutes. And then what we're going to do in the crosstalk is to discuss a couple of those incredibly frustrating moments that have made all of us want to throw our computers or other technological wonders out the window. And we'll talk about the relevance of our work to making the situation better and perhaps lowering your blood pressure. So I'm going to begin with a short discussion of my own work. The underlying theme of my research for the past many decades has been to make computer systems easier for people to use. I started doing that with what was called computer-aided instruction in the 70s, and I'm still doing it. In the last decade, I focused in particular on modeling collaboration and teamwork in order to make computers smarter about how they interact with people, to use those models in decision-making and in their communications with people. This research focus emerged from my early work on natural language processing and dialogue systems, getting computer systems to interact in the languages we speak with people the same way people interact with each other when they're doing something together. You might ask how I got from natural language to collaboration, and that's through a computational model of dialogue that I developed, which had two components that were shown to influence the linguistic forms of dialogue. One of those was attentional state, and the second was intentional structure, that is, the structure of the purposes of the various portions of the dialogue. It turned out that neither speech-act theory in philosophy nor artificial intelligence work on planning and planning systems was sufficient as a basis for modeling intentional structure, and in both cases for a rather simple reason. Both of those ways of approaching understanding language and action and planning were very individualistic in nature, so actions and intentions were seen from the point of view of an individual. And dialogue is inherently a group behavior, so they were insufficient for supporting modeling group behavior. The particular model of collaboration that we designed, which we call shared plans, provides a specification for the beliefs and intentions that are required for collaborative action. So from the perspective of a computer scientist and building better systems, this specification says what a computer system needs to know and what it needs to commit to being a good team player. Included in these specifications are commitments to a common goal and to doing one's part to make sure the team can succeed in reaching that goal. There's also a constraint that the division of labor, that is the assignment of different subtasks to different agents or people, be one that's appropriate to the skills of the team members. That is, you can't assign an agent a task if it's not able to do it. Now, that might seem rather obvious to you. On the other hand, most of the systems that make mistakes by popping up dialog boxes or interrupting you at the wrong time or making suggestions that make you think, why on earth would it think I want to do that, are behaving this way because they're trying to do something they don't know enough to do well. For those of you who remember the Microsoft paperclip, it had exactly this problem. It was overreaching its knowledge. One of the things I'm looking into this year is how to get this right in health informatics systems. For computational reasons, shared plans also has a constraint that only the people doing a subtask need to know the details of how to do that subtask. So it's rather obvious why you would want that to be the case. I'm sure you would all be rather upset with a student or co-author who wanted to tell you in nitty-gritty detail every step of what they were doing to do their part of something. There's also, from the computer scientist's point of view, there's much too much information to communicate and deal with, or we would say it's computationally too complex for a system to operate that way. So you don't need to know everything that your partners are doing, but sometimes you need to know something about what they're doing, and sometimes they may have information that's helpful to you. What I've been doing with my students the last few years is to examine just when those moments, how you could compute just when those moments happen. When is it appropriate to interrupt a teammate, either to give or to ask for information, or to offer or to get help? For a computer system to be a good teammate, it's got to do that right. This is, again, something that I'm interested in with respect to health information systems. There are many reports of doctors being completely desensitized to the drug warnings that pop up because they pop up too much. So how do you time that right? So what may be less intuitively obvious is that computing the value of an interruption, that is, computing the value of the information you might either give or get, or the value of a helpful action to a collaboration, is also computationally very complex. And that's one of the focuses of the research in my group, and I'm going to say a little bit about that in a minute. The other thing we do is so that's kind of the science of what we do. We also are interested in taking the general principles of shared plans and applying them to the design of what we call collaborative interfaces. So this is using kind of using the specification as a kind of inspiration. Okay, so let me just give you an example of the scientific work we've done. We were interested in people's willingness to accept interruptions when they were involved with a computer system in a task that was occurring in a world that's rapidly changing. So you can think about a computer system that might be assisting a rescue operation. In order to determine the net benefit to the collaboration, you need to analyze what the collaboration would do if the information were exchanged, as opposed to what it would do if the information weren't exchanged. But the world's uncertain. There's a mathematical framework called Markov decision processes that's appropriate for working in situations where outcomes are partly random and therefore not under the control of the decision maker. These are very efficient for single agent actions, that is, for planning the activities of a single robot or a single computer agent. They seem like a natural method to use in this case. There's a hitch, though, which is that when you generalize them from the single agent case to the multiple agent case, they become intractable. That is, it would take lifetimes of the universe to compute what to do. So you can't just use these generalized Markov decision processes. What we did in our work was to leverage one of the characteristics of shared plans, which I told you about, namely that the different individuals working on a task need to know the details of what they're doing, but not the details of what someone else is doing in general, in order to define a new type of MDP, which we call a nearly decomposable Markov decision process. Essentially what that does is separate out the work of the individual agents, which is what you're doing much of the time, even when you are collaborating, from those points where you need to communicate or you're doing something jointly. By doing that structural separation, it lowers this model lowers the complexity significantly. So that's the model. We then use that model to investigate, as I said, the conditions of acceptability of interruptions. And I'll just give you one of the results we got, which is that people are equally willing to accept interruptions from people and from computer systems if the perceived net benefit is large, and to reject them equally if the perceived net benefit is actually negative. That is, the cost of the interruption is greater than the benefit. Where they differ in their willingness to accept interruptions is when the net benefit is small. And in those cases, those kind of borderline cases, they're more willing to accept interruptions from people than they are from computer systems. So that's one kind of work we do. The second kind of work, as I mentioned, is to apply these techniques to the design of what we call collaborative interfaces. And we've done that in a couple of different arenas. I'll just mention two. One is a system called SCAS that built a collaborative interface for teachers and students that was layered on top of a program for teaching middle school students statistics. Essentially, what that does is watch over the shoulder of the students doing the statistics to notice what they're doing. The particular system they're using allows them to explore. This is one of the new things in pedagogical innovation, is to allow students to explore different approaches. Well, middle school students do several things when they're playing with this. Some of the time, they're trying to solve the problem, and they get it right. Sometimes they don't get it right, and sometimes they're just playing around. So that presents an interesting computational challenge for recognizing what their actual plans are, which actions fit into working on the solution appropriately, which ones are mistakes, and which ones should just be ignored as playing around. So we developed a number of plan recognition algorithms and ways of presenting to teachers what the students were doing. So I'm going to stop there with those two little tidbits and say I'm happy to talk about either the science or that use in collaborative interfaces during the Q&A. I'll just mention that another piece of work that has just started in my group, it has shown that agents displaying an emotional stance toward a situation makes computer agents, when they're working together, work more effectively. And it also makes computer systems more appealing negotiating partners for people. But about this, my partner here, Cliff, can say a lot more. So, Cliff.
Thanks, Barbara.